Hello, class. It's Miss Thibodeau.
Or is it Mr. Athyde? Yeah, that's right. I'm just tagging in here to lead you through characteristics of polynomial functions. Let's get straight into it. You talked a bit about general shape of linear, quadratic, cubic functions. We're going to get a bit more specific about the graphical representation of each function type. Now, some vocab we need to be familiar with as we go through this so that we can discuss the concepts. You're familiar with plotting things on a grid. This grid is the coordinate plane. It's the crossing of two number lines, right? The x-axis itself is a number line with 0 and 1, 2, 3, 4, 5, 6, etc. And the y-axis itself also a number line with 1, 2, 3, 4, 5, etc., etc. And the crossing of those two number lines creates this two-dimensional region. They're drawn perpendicularly to each other, the 90-degree angle there. And we use x for horizontal axis, y for the vertical axis. The place where they intersect, right there, where y is 0 and x is 0, has a name. That is called the origin. And again, it's the spot where x is 0 and y is 0. So its coordinates are 0, 0. When we talk about the regions in this coordinate plane, there's like 4 different regions here because of the crossing of those two axes. And since there's 4 of them, they are called quadrants. The order that these quadrants are named in might seem a little wonky, but it starts with, of course, quadrant 1 here, and it's kind of like taking some angle arm that exists. Let me just erase this. And then rotating it around this way. And as that goes through, we get to a new quadrant each time. Woo! So again, sorry as I rotate this some more. As it starts, we go into quadrant 1, and as it continues rotating in that counterclockwise direction, there's quadrant 2, and it keeps going into quadrant 3, and it keeps going into quadrant 4 until the cycle completes and it's done. So that's the directionality aspect of the naming of these quadrants. So quadrant 1 is top right. You can note that to get into here, we'd have to move right and up. Moving right means x is positive. Moving up means y is positive. To get into quadrant 2, we have to move left and up. So if we're moving left, x is negative, and moving up, y is positive. Getting into quadrant 3, we have to move left and down. So since we're moving to the left, x is negative, and moving down means y is negative. And then finally, to get into quadrant 4 anywhere, we have to go right and down. So since we have to go right, x is positive, we have to go down, y is negative. And that's what's listed for you here in these bullet points. With these polynomial functions, one of the characteristics that they'll all have is some kind of end behavior. And when you talk about end behavior, it's what's happening at the ends. Now, they go on infinitely infinitely in the left direction, in the right direction as well. When we read the graph, though, when we talk about end behavior, we are always going to read the graph from left to right. So similarly, when we talk about end behavior, we're going to look at what it's doing on the very, very left. If this graph just went on forever and ever, like toward negative infinity, and then continue it on to the right side, follow it as it goes on forever and ever towards positive infinity. So as those x values change from left to right, from negative to positive infinity, what quadrants are we going from? So on the left end, where is it finishing? And on the right end, where is it finishing? And the way to state it will always be as going from one quadrant to another. So for example, quadrant 3, to quadrant 1, where that would be left side for quadrant 3 and right side for quadrant 1. Worth noting, left side kind of has to be quadrants 2 or 3. Right side kind of has to be quadrants 1 or 4. Take a quick second, see if you can state what the end behavior is for these two graphs down here. Feel free to make a guess. There's lots of room here. Pause the video for a solid minute. And then after those 60 seconds are up, resume. Quality pause. Hope you made some solid guesses. Maybe they're educated guesses. This particular function on the left side, it's going way up and it's going to the left. Up and left is quadrant 2 behavior. So left side, quadrant 2. Where is it ending? Well, right side going this way. It is going right. It is also going up. And up means it's going into quadrant 1. For this other relation, left side, this thing is going down and it's yelling timber. And because it's going down, it's going into quadrant 3. Right side, shooting up straight to the sky, and it's finishing in quadrant 1. So the end behavior says it goes from quadrant 3 to quadrant 1. So that's end behavior in a nutshell there. We can also, for polynomial functions, talk about turning points. A turning point is a point where the graph changes direction. So fill that in. Now, when we talk about changing direction, we're not talking about left, right, because we are always reading these graphs from left to right. What we are talking about would be going up or down. So you could imagine somebody just kind of sitting on this, following this path along, and as they do so, where are they going? So this person walking along this path, they're going down. They're going down, 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 down. And then all of a sudden, they reach a bottom. And now they're going up, 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 up. So that person was going down initially. Then they were going up. They changed direction once. So this has one turning point. You may be looking at the next one. You can guess some things as I demo this. But again, picture somebody walking along it, left to right. This person moves along. They're going upward, they're going upward, they're going upward. Ooh, it's a steep climb here, very much upward. And as they continue, yep, still going up. They're getting higher and higher and higher and higher. That person did not experience any changes in direction. They were going up the entire time. So this particular relation had 0 turning points. You are about to do a bit of an analysis. You're going to play around with some polynomial functions in Desmos, which is a fantastic, powerful app. You've got these instructions in front of you. I'm just going to go straight to Desmos and talk about the game plan here. So here's the Desmos graphing calculator. On the left, we've got a box that says 1 and a box that says 2. As we keep adding things, we can just add more and more things to graph. We can get rid of them by pressing their X's, top right of each one of those boxes. One at a time, so not all at once. But you're going to type in the standard form of those functions. So you're going to start with just linear functions and play around with that for a bit. And it says y equals ax plus b. So I type that in. Y equals, oh no, I don't see a. Don't worry, there's alphabet button. You can access the regular keyboard. A, x, and then plus b. And when you do that, it asks, do you want to add a slider for A, for B? Because it recognizes X's and Y's. It knows that's what we're plotting. But it's like, what are A and B? You can just hit all. And now we can actually change those values. You can change them a whole bunch of ways. You can change them by dragging these sliders. So there's A changing, there's B changing. You can also just tap on the number and manually input something. Like, I'm going to make A, I don't know, 10. Or maybe I'll make it equal to 3. Or maybe I'll make it equal to 1 over 2. And that division button turns things into a fraction. You can even just press the pi button and say A is now pi. But you can play around with it all sorts of ways. Set it back to 1 just for funsies, and that thing's good to go. You're going to change those values. So for this linear function, y equals ax plus b, there's just an a and a b that we have for sliders. Play around with it a whole bunch, and then on that next page, see what you notice. Just a quick look at those things that you're supposed to be assessing, analyzing. For a linear function, you're going to see what happens if you have a positive a value. What happens when you have a negative a value. You're also going to check on the domain that you notice. And correspondingly, check on the range. And is that range affected when you have a positive or a negative a value? As you play around with things, see how many possible y-intercepts you could get. See how many possible x-intercepts you can get. And just to go back to Desmos real quick here, note that if you tap on the function itself, dots pop up. Dots are some kind of critical point in general, or very important, useful point. We can tap on those. The intercepts will always be highlighted in Desmos. That's something we can always find. You can see that this has an x-intercept, which is where we're hitting the x-axis. It also has a y-intercept, where we're hitting the y-axis. So you're going to go through all that with the linear relations. Really mess around with these numbers a lot. Try positive numbers, try negative numbers. Try whole numbers, try fractional numbers. Try all sorts. And once you've filled in the entire chart for linear, then switch it to quadratic. And on your sheet, listed for you in case you forget it, but it's ax squared plus bx plus c. And adding that c, it says, do you want to add a slider for c? Sure, of course I do. So I add that in there, and again, play around with these sliders. What happens is a gets big, as it gets small, as it's fractional, or as if it becomes negative. What happens to c as c becomes bigger or smaller? What happens as b becomes bigger or smaller? What path is it following? And what features do you notice in each of those cases? Again, you can tap on the function, check out the x and y intercepts. We can also note the vertex of the quadratic. That's something that gets highlighted in Desmos. And same when you look at cubic functions. So ax cubed, plus bx squared plus cx plus d. Again, it's going to ask you if you want to add a slider. Of course we do. And we're just going to play around with those values and see what happens as we do so. Whoa, all sorts of crazy things. It's cool. But see what you notice. And again, tap on it to see important points. We can see on this one, it's got some sort of low there, some sort of high. It also has intercepts that we can tap on. So we can always check those out to see what's going on. Don't forget, you can zoom, you can pinch zoom, you can go in. You can also note that if something's way out of range to see, you can always just zoom out a bit to see the aspects you're looking for. So zoom in, zoom out, whatever it is you need to do. But really be rigorous with this. You want to try lots of different examples to test your observations. And that's written right here. So it means checking your ideas more than once, not just seeing what happens the one time and saying, yep, that's going to happen every time, but seeing if it holds true in other situations. If you have a positive a value and a negative b value, or negative for both, or the other way around. but always recording what you notice, and whatever you think is happening, does it hold up to scrutiny? And that's what you're going to try and document on this next page for all of those. Videos coming to a conclusion here. Your task for the remainder of this class is to complete this table. And only once you have put in that high effort of completing it to the best of your abilities, actually going through it and genuinely engaging with Desmos there, then check out the answer key on Teams, see how it compares to what you've observed, what you've noticed, circle anything that might differ, highlight any misconceptions, make sure you have questions written down if you need to get them addressed. And other than that, you've got instructions from Miss T, so look forward to those. I'm out. Goodbye. Stop.